Yeah. So now in the last video we discussed about Heidelberg limits and the Friswell index. So those two tests doesn't give the load bearing capacity of the soil. So now to identify the properties which are required to lay in the field, what we do two important tests. One is Standard Proctor Test, other is CBR test. Now what is important Standard Proctor Test? This Proctor Test will indicate you to what maximum density you can compact a given soil into a field. So whenever you compact a soil, you need to compact the soil at a maximum density so that we get a better load bearing capacity and also very less amount of voids. If voids are there in the subgrade, it can accumulate water. So to avoid all those things, we need to compact at the maximum density. Now to find the maximum density, what we do? We need to find optimum water content. So now the maximum density can be achieved in a particular water content, what we call as optimum water content. So now how to do this experiment? What we do basically, we take a soil mass, right, of known weight, and then we add the water at some percent of soil mass. Then we keep increasing the water content at different percentages, let's say 5, 6, 7, 8, 9, 10, and then correspondingly we will determine the dry density by compacting the soil mass in a standard conditions. For that we use something called as Standard Proctor mold. Standard Proctor mold. Then we take a 2.5 kg standard hammer. So what we do basically, when we mix the soil at this particular water content, let's say, then we compact the soil in the mold in 3 layers by giving 25 blows per layer with this hammer. Right? Similarly, we fill the mold by compacting 3 layers, 25 blows. That means if this is a particular mold of given volume, we fill in 3 layers, right? And each layer has 25 blows. 25 blows. So after this, once we know this, we'll take the weight of the soil. So we know the volume of the mold and we know the mass of soil. We can find the wet density. But to find the dry density, what we do? We'll take some portion of soil, right, some grams of soil, and keep in the oven, right, for drying, and then find the dry density. This exercise is repeated for different water contents. Now let's say 5%, 6%, 7, 8, 9, 10, 11. Now for each water content, right, we have data of wet density, dry density, and then also water content. Now we will develop a plot, right, this moisture density relationship, and then we will get a curve in this pattern or this fashion. So if you see this particular value here, so wherever this curve is changing direction from right upward to downward gradient, there is a point where you get the maximum dry density, right? So this is the maximum dry density and the corresponding OMC. So now this is called as the dry side and this is called as the wet side. So what happens as we increase the water content slowly, there will be increase in the density because the soil is lubricated and properly get compacted. But what happens later, once the optimum density is achieved, where there is no voids, completely soil mass is there, almost 0% voids. So what happens when you increase water further, right, on the wet side, the water will start filling the air voids. They will start filling the space between the soil and hence the density start decreasing again. So this is the optimum water content at which we need to compact, at which we need to mix the soil in the field to achieve maximum dry density. So we will show how this experiment is done in the video, right? And the other important test is California bearing test. So now this particular test will give you at what density and what OMC you need to compact the soil in the field. But this particular test will indicate you the load bearing capacity or the strength of the soil, whatever it is trying to show. This California bearing test is a test developed in the California, right, by US Army. So basically this test is most widely used test, right, in any of the highway agencies to find the soil load bearing capacity. So basically what we do, we have a CBR mold. In that CBR mold, we will compact the soil at this OMC and MDD. Right, this forms the basis for this. So we will compact the soil at a known OMC and MDD. But let's say, in case sometimes if you want to evaluate the CBR of the actual field, there what you will do, you will find the actual field density and then you will compact the soil at the particular density. But the laboratory conditions what we do, we will find first the OMC and MDD and OMC and then compact the soil in the CBR mold. Now to prepare CBR sample, what we do, we will take soil from density from the MDD and OMC. We will mix the soil approximately around 5 to 6 kgs, right, of soil at OMC. So we get the OMC water content. So what we will do, we will compact the soil in a CBR mold with compact effort of 5 layers, and each layer 56 floors with a 4.9 kg hammer. So with this compactive effort, we compact soil in five different layers, like this, 5 different layers, 56 loads per layer with this particular hammer. So once we compact, right, what we do basically, now we can have two conditions in this test. One is we can determine, one is called as soaked CBR, other is called as unsoaked CBR. So once you compact the soil, right, when CBR sample is prepared, so now what you will do, you can either determine a soaked CBR or unsoaked CBR. The soaked CBR means what happens, so once you compact the soil sample, the whole assembly will be kept in the water, in a bucket of water for at least 4 days to simulate the soaking. That means what happens, let's say you build a pavement, the pavement is in constant with like water contact. So what happens, the soil, the CBR may reduce, the strength may reduce. To simulate that, so what we do CBR in soaked condition. That means it's a worst case. When there is water in and around the soil, so what CBR one can achieve in the soil. So in the unsoaked, basically, let's say if it's a very dry arid region where you will not encounter too much of water, in those cases you can go for unsoaked CBR, right? So normally, anyways, the soaked CBR is always preferred because it's a worst case situation, right? And so the soaked CBR. So now, once you keep the soil for soaking, right? This is in a bucket of water. So basically, we also keep a surcharge weight. The surcharge weight is kept to simulate the weight of upper layers. You see, the subgrade has a granular base and bituminous layers or a concrete pavement. So now to simulate this weight, so whatever the soil has been compacted, on that soil we keep a surcharge weight of around 5 kg, right? So this will simulate the weight of the upper layers. So once you do this, after 4 days, we will do a simple load deformation test. So we have CBR apparatus which will apply a penetrative load at a rate of 1.25 mm per minute. That means there's a plunger. The plunger slowly penetrates the soil, right? The wet or soaked soil at a rate of 1.25 mm per minute. So during that time, we will record the deformation at particular defined deformation values and note the corresponding load values. So there are some particular deformation values given like 0, 0.5 mm, 1 mm, 1.5 mm. So corresponding to those, we will know what load one achieved in the CBR test. Then you will plot a graph, a load versus deformation plot. So while doing this kind of plot, you may get two conditions. So one is this case, the other is this. So normally you may get two kind of graphs, right? So basically what we do now, the CBR. So basically CBR is a ratio of load carried by soil corresponding to or at 2.5 mm penetration divided by load carried by standard aggregates at same 2.5 mm penetration. Normally for 2.5 mm we have a weight of 1370 kg. So let's say whatever values you get, right? Let's say if it is 500 kg, 500 by 1370 kg at 2.5 mm penetration. So this is 2.5. Corresponding to 2.5 mm penetration, you will find the load taken with a soil sample. You will record the CBR at 2.5 mm penetration. Similarly, again you will take one more value at 5 mm penetration. Then report CBR at 5 mm. Right? CBR at 5 mm. But the report to find the standard 5 mm penetration, this will be, let's say, y divided by 2055 kg. So at 2.5 mm you have 1370 kg. At 5 mm you have 2055 kg of standard load, right? The load carried by standard aggregates at this particular penetration values. So then you will report whichever is normally the CBR 2.5 mm will be higher than 5 mm. We will take this as a particular CBR value. But sometimes what happens when you plot a graph of load deformation, initially the shape may be a different, it can get different curvature. Then what you will do, you will shift this particular curve backwards by drawing a tangent. It should be backwards in this fashion, and this will be the origin. So initially for this particular graph, this was the 0. But for this, when there is a initial curvature in the plot, then you shift the readings back and draw a tangent and will connect the line to the x-axis, and this will be your 0. From this we will measure 2.5. In that case it will be somewhere here. This will be 2.5, let's say, and then you correspond to this particular value. You will find what was the load carried and then find the CBR values. This is called a CBR mold. Again, this is the CBR. This is a mold and this is a collar. So this collar can be lifted, right? When you want to lose the soil, when you want to remove this particular this one. This is a collar. This is the soil what you will compact. This collar is used to just in a compaction. When you want to compact the loose soil weight exceeds the height of this particular mold, this will support the soil. Now, once you compact the whole soil, what you will do? When you place this whole assembly, you place this whole assembly in the water and you place this particular annular ring on the top of the soil, so that this particular annular ring will simulate the weight of the other upper layers in the subgrade.